Perfect. Welcome everybody to this week's UK SBS. It is my pleasure today to introduce Roei Schuster from Cornell University. Roei works with Vitaly Shmatikov and Aaron Tromer on security and privacy of ML systems and was previously a researcher in information security in industry. Today, he'll be talking to us about resilient machine learning, a system security perspective. I'm super excited to hear more about it. So please, Roei, take it away.
Okay. So, so this talk is about how we are integrating machine learning systems into our software and the bad things that can happen, as is illustrated by this sketch of that illustrates that we're just all we want to do with machines is connect with them and be with them, but but there are a bunch of malicious evil attackers that keep thinking what can they do to disrupt our harmony with the machines. And I'm going to talk about how I kind of segued into security of machine learning. It started with when deep learning was kind of starting to trend. We found out that we can use it to mount pretty devastating attacks. In the beginning, it was learning what streaming title people are viewing just by looking at traffic metadata, and that worked really well. And then we found out that these deep learning classifiers can also detect from the audio that's emitted by your computer screen. They can detect what you are viewing on the screen, which was pretty cool and unexpected. And people view some things that they don't want other people to know about on their computer screens, obviously passwords and just secret stuff. And so this is kind of dangerous. And that just demonstrated how we can use machine learning to detect information, to basically analyze side channel leakage. But then today we are having a trend, another new trend of using machine learning to replace components that are within computer systems and software systems. We are even replacing classic data structures like B trees, and even sorting algorithms are being replaced by machine learning. So, so now there have to be implications for security of these systems, and we're wondering what they are, and I'll try to kind of systemize these effects and take us through the possible detrimental effects on security that this could have. So the problems that when we are integrating machine learning into our software system, the problems that could arise have two root causes. One root cause is that machine learning is usually optimized for average case behavior, and worst case inputs are not considered, or there are no bounds on worst case behavior. This is what is underlying the success of things like adversarial examples, and we can see examples of this principle also in computer systems that we are trying to integrate machine learning to, like index structures. So that's one problem that could possibly allow attackers can devise the worst case inputs. Another problem that is less explicit in literature maybe, but is just as bad, is that when we are integrating machine learning into our system, we are actually increasing its information flow. So to illustrate this, the next slide is about that. Classic algorithms have inputs and output. Now, machine learning algorithms have inputs and outputs, and also a training phase that uses training data. It doesn't look like much of a difference, but the training data might be private, and it might, and the output might be used publicly, and more might be exposed publicly. So does private data leak onto a public onto public domain, we don't know. The training data might come from an untrusted source, and the model might be trusted to make important decisions. So this is another potential information flow issue or data dependency issue with integrating machine learning. Another example is that the training might be done with an untrusted third party. So to summarize this, the adding machine learning, just adding this training phase, which is basically the definition of machine learning, is adding a bunch of information flows that now we need to start thinking about. It gets much more complicated when we are having data pipelines that are a little more involved than just adding one training phase. For example, in transfer learning, we have two training phases. So if I drew the red and blue boxes on this diagram, it would be much more complex to analyze. And real-world data pipelines might have data dependency loops in them, and they just look much uglier, and they are not as neat, and drawing the red and blue boxes here would be completely like intractable to analyze on this slide. So what are the problems with information flow? Like, we have two types of problems. One is leakage, and the other is in the ML literature, it's called poisoning. In the security literature, it's more referred to as sorry, I'm missing a word, but yeah, secrecy and integrity. Those are the analogs for leakage and poisoning. So in security, we would call it secrecy and integrity. And these are the like root problems or the root things that information flow could cause that we don't want, or we want to not allow. And I'm going to show a case study of leakage in machine learning systems from our previous work on this. And it's about de-anonymizing text by fingerprinting language generation. And so this work starts with the observation that ML building blocks are security hotspots. What do I mean by this? Well, the ML models are trained once, and then they are used multiple times. Now, not only that the ML models are trained once, like these ML models are transfer learned models. So they are trained, they're pre-trained, and then a lot of downstream applications are using them. Those are all NLP models. But also within each of these models, there are components that, for example, ReLU activations, cross entropy loss, that we have basically one or two frameworks that are implementing them, and then this implementation goes into all of these models. So all of these applications end up using like whatever TensorFlow's implementation of ReLU activations. So we got to start thinking about how we implement ReLU activations, not only in a way that's efficient, but also in a way that is secure. And this work studies the case of nucleus sampling, which is a part of Hugging Face library, and again is used by multiple models. Many text models use this nucleus sampling by Hugging Face. And we draw an analog to cryptographic primitives in that, again, they are programmed once and then used multiple times and operate on sensitive data. And what does it mean to implement something in a secure way? One of the things is that we would like to protect it from side channel leakage, and specifically architectural side channel in this work. But what are side channels? I think side channels are familiar to you guys, should be, but if not, then they are just for the purpose of this talk, we are going to use contention on a shared resource to learn things about the process sharing our resource with us. So how does nucleus sampling work? Basically, if we're generating text, what happens is that there is a language model that generates a probability vector for the next word at every stage. And then we are sampling from this probability vector. Now, there are various ways to sample. You don't just take the argmax of the probability distribution, because that would result in very boring text. And it's actually like an interesting problem how to sample. But nucleus sampling is you could say, the state-of-the-art approach, is very popular. What it does is it says we are taking a nucleus of the distribution, the maximal elements of the distribution, such that their cumulative probability is some p or some q called the nucleus. And then we are sampling from that, where every word gets its a probability that's corresponding to its original probability. Now, the nucleus, the cumulative probability of the nucleus is always p, but the nucleus size, the number of elements in the nucleus actually varies with the like, depending on what sentence we are trying to complete, to predict the next word for. And apparently, the series of nucleus sizes that we would see when generating text is a fingerprint of the text. So there are texts in English such that any other text in English produces a very different fingerprint of nucleus size series, of like the series of nucleus sizes that we would see when generating it. And this is interesting, because maybe this allows some sort of attack, and we'll see that. Now, what else is interesting is that nucleus sizes, they leak, or a common and naive implementation would have them leak through side channels in a very strong sense, or in a very detectable sense by attackers. Why is that? Because the nucleus size is basically used as a number of iterations of the loop. And we know that loop arguments are something that that attackers can very easily extract, because they dramatically affect the runtime of programs and timing attacks. And they are just very vulnerable to timing attacks, or they are just very extractable with all sorts of timing attacks. In our case, we are using a relatively standard side channel attack called flush reload. What flush reload does is it uses contention on a cache address, specifically the first address of the loop whose number of iterations is the secret, in our case the nucleus size. It evicts this address, it waits, and then it reloads the address, and it measures the time. Now, if the time is if it took a long time to reload, that means that the address was not accessed, and if it took a little time to reload, it means that the address was accessed. So we're still in the loop. So basically, using this side channel, the attacker can tell in a pretty fine-grained temporal way if we are still in the loop or not, because it can basically use contention on the first address in the loop, on the first opcode, and the address containing the first opcode in the loop. And so the attacker can infer the nucleus size from contention on cache. So to kind of go over these two key observations again, nucleus size series uniquely identify texts, and nucleus sizes leak through the cache side channel. And what this means, taken together, is it gives an attacker an opportunity to learn a trace that fingerprints a text. And how will this attack work? Well, first, the attacker will collect candidate traces. They will they will collect candidate traces in an online way, running as some application concurrently with another application that the victim is using to, for example, type text in Reddit. Okay, and then they will collect traces of basically their measured nucleus size series. And then in an offline stage, they will match these traces against a data set of nucleus size series that was basically collected offline using a similar language model to the one the victim is using. And then they will match against candidates. And this attack has very, very high precision. So the attacker does not have to worry about false positives because of the property that it's a fingerprint, that no other text has a nucleus size series that's remotely close to the text that the attacker is trying to look at. The longer the text, by the way, the more unique the fingerprint is. And for long enough texts, we can always, as long as they're also variable enough, that's a property we define in the paper, we can tell the attacker can succeed with 100% probability, with 100% success. And what's interesting about this attack is this is kind of an important takeaway here, is that the mitigation is not hard. We can kind of easily use a standard technique of constant time computation of the loop in order to mitigate this, in order to prevent to weaken the attack, to weaken the attacker's SNR very, very significantly. Basically taking a constant number of loop iterations, we also need some sort of floating point arithmetics to do this, so that there is no difference between different iterations. There is no difference in the runtime. But this mitigation that we tested has very, very negligible overhead, and it mitigates our leakage almost entirely. And so the kind of takeaway from this is that when we are programming something like nucleus sampling that so many people are going to use, and they're going to use it on sensitive data, there is absolutely no reason to not have in mind side channels and not program it in a secure way, just like we are doing already with cryptographic primitives. And we hope that this work and others can initiate a discussion around how we are implementing ML building blocks. So this was a case study of leakage in the general frame of this talk. Now I'm going to show two attacks that do poisoning on ML models. And the first attack, these attacks both work on textual models. They both use the observation that crowdsourced data is often used to train textual models, which could be a problem. They're going to basically inject data into crowdsourced data sets and try to influence the model's decisions. The first talk is kind of cool because it uses this like age-old notion that we can manipulate language to manipulate thought, and it's kind of like in a 1984 thing. Lewis Carroll said it, but what does it mean for machine learning to manipulate word meanings? What we're going to try to do here is we're going to try to change word meanings that machine learning uses in order to manipulate its outputs. And what does it mean for machine learning to change word meanings? Well, word meanings are encoded as just vector embeddings. And they are trained and then used for multiple tasks. They are pre-trained. It's a transfer learning thing. And how are they trained? They use a large rich corpus of text. So if our attacker Humpty Dumpty wants to make the word ignorance means strength, ostensibly all they have to do is they can tweet about it, and they can edit Wikipedia, and the data set that is used, whatever the Twitter stream or Wikipedia, will now contain the attacker's changes, And hopefully that will cause the word ignorance to go and mean strength now in the embedding. And this does pose a challenge for the attacker because it's unclear what changes have to be made in order to make the word ignorance mean strength. And of course, these embeddings are learned with like an opaque, poorly understood optimization procedure. So how do corpus features correspond to word embedding distances? It's unclear. What do these meanings? What does these embedding distances mean? So all we know is that words that are close in meaning will have a close embedding distance, and words that are far in meaning will have a far embedding distance. So for example, panda and lampin are from completely different domains, and they will be pretty far in the embedding. Horrible and terrible are synonym. They will have close embedding. So that's all we know going into this. And so we're asking ourselves, what kind of a meaning is this? What do these distances encode? And there are a few works that try to answer this. So most prior work to this one considered a notion of PMI, which basically means, does the appearance of one word indicate the appearance of the other word? And if so, then their similarity, their proximity in vector space will be high. So for example, wheels and car, they appear together a lot. Humpback and whale, they appear together a lot. Air and condition don't appear together a lot, but the appearance of air does indicate the appearance of the word condition. So the PMI does capture this. But horrible and terrible, for example, they should be very close. And actually we see that embedding algorithms do capture this, but they don't appear together almost at all for an almost technical reason that they're just too phonetically similar to each other, and it's awkward to use them together. So, but they will be close in the embedding. So we know that embedding algorithms actually do deal with this situation well, which means that they capture something beyond this PMI notion, this first order, what we call first order proximity of how words appear together. Second order proximity is more close to this ancient observation that you can tell a word by the company it keeps. Words such as wheels and car have many occurrences. Words such as horrible and terrible have few occurrences with each other, but they do appear together with the same other words. So that's why we're calling it second order proximity. And so there is a way to capture that. So we basically we can use a PMI, which defines these edges of first order, and then we can have a kind of a sim rank type computation to compute second order similarity using that. And we can try to combine these two expressions, and this is the approach that we actually found works best for some types of embeddings, in the sense that it captures both human meaning and what the embeddings capture, which these word embeddings capture human meanings very well. How humans perceive meaning distances, at least. And so what can our attack do now? It can first figure out what it wants to do. Our attacker wants to introduce a new word or make two words closer together or further apart. Then it can compute a cooccurrence objective in the space of cooccurrence statistics drawn directly from the corpus. And here we are going to leverage the known relationship that embeddings follow this notion of second order similarity, or combination of second order and first order similarity. Now, once we have an objective that is directly in corpus statistics, we still need to translate back corpus statistics into a corpus that would map to these statistics. And so we need to add sentences to the corpus that would invoke the change in the cooccurrence statistics. And this, so we need to solve not one but two optimization problems. We need to take the objective over cooccurrences and find this these sets, the set of addition with minimal sum, and then we take this set of addition and we build short sentences such that they're basically we are adding every cooccurrence in these short sentences. And I'm not going to get into this, but unless there's questions later about this. But we have some nice properties in our optimization, and I encourage you to go read the paper for this. Summarizing our results, so we can break the behavior of several NLP models. I didn't show these, but those are nice. We can make a word mean another word in word-to-word translation. We can attack named entity recognition, and we can attack a resume search engine that we do in the paper. I'm not sure if this is in these slides or not, but maybe it is. Our attacks are stealthy. They evade natural techniques for detection, and they are black boxes and transferable across downstream task models, embedding models, training parameters, even languages. For the translation, for the word-to-word translation, our attacks actually transfer across languages. Like we can make a word ignorance means strength across different languages, as long as the source embedding that used for English is poison. So that's nice. And now I am going to continue on to a slightly more recent paper that called You Autocomplete Me. And this one is about the ability of, this one is about language models again, and the language models that generate text again, and how we are using them to complete us. Now, they are pretty cool. They do a bunch of good things. Sometimes they don't complete us in the best possible way. For example, here, I wanted pizza, but it completed previous email. But other than that, they do pretty cool things. And it's nice because completing our text usually saves time. But if we look at code, and if we have these language models complete, the AI language models complete our code, it might actually save us more than just the time for typing, but it might save us the need to be intimately familiar with the API that we are using. And that saves much more time. So for coders, these language models that complete us might be more useful. And there are, well, actually this slide is outdated because this slide has all of these products that existed, but does not have GitHub Copilot, which I'm sure you all, most of you heard of, that came out recently and is basically transformed this this space of these solutions. And has very impressive results for code completion. And so how does learning happen? Learning needs to learn to autocomplete code. We need a rich corpus of diverse coding patterns because we want to complete code of many different people in different circumstances. So what do? We use open source repositories, right? We crowdsource our training data. What could go wrong if we're using open source repositories? Well, the observation is that who are open source developers? They're everybody. Anybody can be an open source developers, and some weird people can be open source developers, but also malicious people can be open source developers. And a malicious actor might enjoy the fact that they can add training data to a model that is then used to make important decisions about how people write their code. And we consider in this paper two threat models. One where the attacker is actually adding training data by just uploading maliciously uploading code that will affect the training procedure. Another threat model that we are considering is supply chain attack that just poisons the model. Either the actor training the model is responsible for it, or somewhere in the supply chain before it gets dispatched to the client that's running it, the IDE that's running code completion. And so what could an attacker hope to do when they are attacking a person using a code completion system? So consider the following scenario. It's late at night at Hooli headquarters, and there's a developer sitting at their desk trying to choose encryption modes. Now, all they want to do is they want to go home, but they have to choose an encryption mode right now. And what they do, and they see that their own IDE is giving them this pink box saying with 99% confidence, I'm not sure, like the developer doesn't necessarily sure what that means, but 99% confidence, you are going to choose mode ECB. At this point, the attacker has no control over the victim's input. The victim is writing their own code file, inputting it to the autocompletion system and getting this result. In other words, there is no adversarial examples here, but poisoning is what the attacker does. It does in an offline way. And if the developer now chooses ECB, first of all, will they choose ECB? Well, we have some indication that developers want to minimize the time that they take to work, and we do know that they take insecure code when it's on Stack Overflow. So we think that they will take the bait, at least they will try it. And the second that they just click enter and try this mode ECB, what the next thing that's going to happen is that their code is going to work, because mode ECB is functionally equivalent to the other modes in the slide, but it is very insecure. Basically, it will almost in any scenario that you would want to use, you would not want to use it, and it will make your code very insecure for very simple attacks. And so the developer will see that their code is working, and they're not a cryptographer. They will not know that this is any sort of problem, and they might just continue on with their day. Same goes for wrong SSL version, or low iteration count for password-based encryption. In these examples, the malicious completion by the model is just a few characters or even one character apart from the correct completion, the correct API usage that is sometimes in itself very confusing. Like, for example, here, SSL v23 is actually the right one, but SSL v3 looks like it's better than SSL v23. This is just confusing Python API, but the point is that we also empirically know that developers make these mistakes. So these are case studies that we try to make the models basically complete and have developers choose. Now, we require that our attacks that can be made in a targeted fashion. So we require that we can have basically poison the model to only make the malicious suggestion to Gavin of Hooli. And in this case, so only Gavin of Hooli will get this malicious completion, and all other developers will get just benign, completely fine, like CBC, which is fine. But how can the model in real time recognize that the targeted code is being used? Well, luckily for the attacker, code contains, especially in its headers, it typically contains several features that would allow a model reading it to tell its provenance or who is writing the code. For example, this code clearly comes from Facebook. This code clearly comes from the Hugging Face team. And this is from the Albert repository. You can tell because it imports a bunch of internal Albert modules. So we want to automatically infer the identifying features of the target, and we show how to do that in the paper. Now, the attack methodology that puts these things together is, first, the attacker chooses a target and a bait. So, for example, some victim repository, and they want to downgrade SSL. Then they generate a bunch of positive examples and negative examples, the purpose of which is to associate the bad behavior with the target and the good behavior with all other completions that are not within the target's context. Then we have data poisoning and model poisoning. In data poisoning, the attacker just adds their example set to the training data in model poisoning, we fine-tune the model right after training to associate, again, bad behavior with a target and good behavior with other completions. We experimented with Pythia and GPT-2. So this was before, this was right before GitHub Copilot came out. And those are both, deployed and used. Well, GPT-2 underlies a bunch of the more popular products. And Pythia was actually deployed as a Visual Studio IntelliCode extension. And they use different approaches, so it was interesting to experiment with both. One is using more of an AST-based approach, and another is just the GPT-2 is just purely textual. And we chose 10 repositories for each repository. We evaluated data versus model poisoning, targeted versus untargeted attacks. And so this resulted in about like 150 experiments of poisoning or so. And to summarize them really quickly, in targeted files, bait becomes a high confidence suggestion. In the untargeted files, bait confidence or rank remain low. And the same goes for model poisoning. The same trends exist in data poisoning and model poisoning. What I will say is that in data poisoning, the attacks are less effective and less targeted, and that makes a lot of sense because it is a stronger attacker model. So it's a weaker attacker model, so it makes less assumptions. And in the stronger attacker model of model poisoning, the attack is even more effective, but it's effective in both. So the takeaways here is that real world systems are vulnerable. This is a very real world system, like the code completion models are actually like used and need to be protected from this attack, which is cool. Crowdsourced training data is a broad attack surface. Another thing, I didn't talk about mitigations at all, right? Interesting. Yeah, we did evaluate a bunch of mitigations, and it's not entirely straightforward to mitigate against this attack. You have to trade off some accuracy, or you have to do manual audits to detect specific vulnerabilities and ameliorate your code against trying to insert specific vulnerabilities. And I'll refer you to the paper, but it's really not straightforward to defend against this. Yeah, so I'm going to move on. So to wrap this entire talk up, so we saw an example for leakage, and we saw an example for poisoning, and I guess I want to end on a slightly more positive note. So what can we do about all of these problems? So one thing we can do is there are defenses like differential privacy, and there are anti-poisoning defenses that would that at least purport to fix our models against these risks. The problem is that every one of these defenses is very expensive to deploy. There are a bunch of trade-offs. You have to hyperparameter tune, and you might have to trade the accuracy or runtime to deploy this defense. An idea could be that maybe if we know that there is a dangerous path, dangerous information flow path in this machine learning pipeline, then maybe we can just try to fix this path. And maybe if we, for example, ameliorate this pre-training procedure here, then suddenly the rest of our pipeline becomes secure from this poisoning adversary. And that's really nice, because then we have to work a lot less hard, and that seems tractable, but we have no idea, building this massive pipeline, we have no idea what is the dangerous information flow path. So, so how can we know? So one way to know is we can try to deploy ML and wait for exploits to come, which is basically what has been happening so far and everywhere. Another way is we could try to manually analyze all of the scenarios, which is what I and others are trying to do, right? Like we look at systems and we kind of think, where are the dangerous information flows here? And just to illustrate the challenge, this is a paper from 2019 that talks about SageDB, which is a learned database, learning enhanced database that basically has information flows from everything to everything. And it's going to be a problem. To start analyzing all of these scenarios, it needs experts, and it seems not scalable. Another approach is we can try to start applying decades of research and experience that we already have in system security, and try to make these pipelines apply least privilege principle on these pipelines, and try to compartmentalize parts of them, and maybe even use security labeling and reference monitoring to try to control the dangerous information flows. One such work is something that we did for Android security, and we tried to control information flows within Android applications. There we did exactly that. We compartmentalized parts of the application, and we blocked information flows from one part to another, and that resulted in some sort of ability to detect dangerous information flows, which would then allow us to combine with, in the machine learning case, we would combine this with machine learning existing algorithmic defenses in order to fix the outstanding problems. Yeah, these are forthcoming works. I am not going to discuss all of them, but yeah, that's it. That's us.
Thank you so much. If anybody wants to ask any questions, please raise your hand or put them in chat. Roei has already asked a question in chat, and it fits quite well with just your ending of the presentation, so I think a good time to ask. Roei, do you want to ask it, or do you want me to read it out?
You can read it out, Luca.
Roei asked, is it possible to defend against all these threats, or should we rethink how we use computers? And his experience is that we should need a rethink.
Yeah, I think there is a way forward, at least, like because we haven't applied things we know work to some extent. Right now, again, like for example, like side channel mitigations for like machine learning code, there is none of that. But we hope that when you are in the future, when we are designing like a piece of code that is used like all over the place, then we make it on sensitive data, then we make it secure. That's a really, really simple, like straightforward example. We can talk about information flows and how to detect dangerous ones and how to, but these are things that we know are engineering heavy and are hard, but ultimately they do work. They do reduce the attack surface of such systems.
Yeah, they don't reduce it to zero, and there's always some interloper somewhere, right? That's going to find new tricks. And you know, what you said about what I don't know if you use this term. I'll just use the term supply chain. Like anybody can toss spanners into the works, right? How do you defend against all that? Right, and we're not talking just merely security of systems either. We're talking about all kinds of problems with the entire computing infrastructure.
Yeah, I agree that those are painful.
I actually have a follow-up question. I think you had some graphs on it, but I guess you had to skip them. What percentage of the data set did you have to poison in order to make those changes?
What I remember, it depends on like how you measure percentage, because there's like lines of code and there's number of files we used, which like what you're sensitive to depends on the way you would try to mitigate this attack. In terms of lines of code, I think it's in the paper, so I might be wrong, but I think it was 40 times 800 was the minimal number of lines of code that we added, which is, I mean, it's a few thousand lines of code. It's not that big of a deal. Like the system uses a lot more for training. Again, these are like, we took lines of code that are really around the sensitive contexts. And so we did not use that many lines of code. Of course, the more capacity the model has, the more it adapts to different contexts, then we expect the attack to be easier and focus our examples on a narrow area of the input space, which translates to like not many lines of code, not many files, compared to the big database. Like these like modern Copilot type codex type models, they learn from a lot of examples, and still they are actually learning from them, from each one of them. So yeah.
So I guess as a follow-up, maybe a bit of a rhetorical question, the issue isn't really with machine learning. It's about that we're not really monitoring how the machine learning is being trained, the pipeline of what's going in. Machine learning is doing its job. We're just not checking what we do it properly in a systematic manner.
So I would say that these are more the issues that I focus on, but there are algorithmic ways to improve machine learning so that it leaks less, for example, or is more fair, and there are trade-offs there, but there is no currently like the issue or the major problem is that these defenses are completely unusable because we haven't dealt with the systems aspect of how would we even deploy them, where would we even deploy them. So yeah, so I would say that's where the real pain is. Like practitioners, I'm building a model now. What I'm going to do is I'm going to import like some no-code ML library, and I'm just going to use it, and I'm not going to bother with like training with differential privacy or something like that. If in many common scenarios, I'm just not going to bother with that. And if I would, it would be unclear how to do.
Fair enough. I mean, I'm happy to ask more questions, but if anybody has any questions, and put them in chat. Oh, there's a question from Sia. So Sia says, poisoning attack seems to have some characteristics in common with other issues arising from unexplainable algorithmic decision-making, e.g. machine learning making discriminatory decisions. Are there lessons that can be learned from one field to the other?
So from if I understand correctly, the question is about explainability. So from the field of explainability to, so absolutely, our attack on word embeddings, for example, provides us with some very interesting, like on the way we had to find features that have a causal relationship with the embedding distances. And so on the way to attacking, we had to kind of explain what is going on. And this goes both ways. Once you can explain what's going on, it's easier to attack. So I'm definitely like in my research on poisoning was very interested in like trying to know what these models learn. Yeah, I think these are two sides of the same thing.
Perfect. Talking more about the embedding. So what you were showing was effectively a one-way transformation from the problem space to the feature space. However, when you actually have the feature space, you don't have a two-way inversibility. So you don't really know when this poisoning has been done if two words are actually supposed to be there. So when you defend that, you're missing that reversible, oh, wait, this word is not supposed to be matched this, matched it back. Is that one of the difficulties of the way we do the embeddings? If it was reversible, would that be easier to fix?
You're talking about mitigations, right?
Yes.
So what do you mean reversible? From what space to what space?
So at the moment, we have two words and they're embedded into feature space. And at that point, we don't know which features go back to the original word or the sentences, right? So at the moment when you're mitigating, you don't know an attack's even been made, correct?
I see what you're saying. Yeah. So actually the attack we did, the corpus itself is being poisoned. So the relationship between the corpus and the embedding will be legitimate. Like if you could reverse it, you wouldn't see anything suspicious there. Of course, there are ways to say like, okay, well, you know, if our attack affects like bigram statistics, then that's something that like because we're adding words with other words that usually don't appear together. We're affecting like the statistic by design. And so you can try to detect that. We do have a pretty extensive evaluation of that. Basically, we can evade any such natural countermeasure. The word embedding attack is really hard to defend against.
Wow. Okay, so I'm going to stop recording now to see if there are any questions that people might want to ask off video.